close your eyes and imagine standing at the edge of everything, the ultimate boundary, the final frontier, the place where existence itself comes to an end. For as long as humans have gazed at the stars, we've wondered, does the universe have an edge? Is there a place where space simply stops, where you could reach out and touch the boundary of all that is? Tonight, we embark on the longest journey imaginable, a voyage from wherever we are to the very edge of the observable universe, 46.5 billion light-years away. We'll travel through galaxies and cosmic voids, past the limits of what telescopes can see, to the most distant light that has ever reached Earth. We'll explore what edge even means in a universe that may have no center, no boundary, no edge at all in any conventional sense. This journey will take us to the cosmic horizon, not an edge where the universe ends, but a boundary beyond which light has not had time to reach us since the Big Bang. It's an edge created not by space running out, but by time running short, by the finite age of the universe and the finite speed of light. Beyond this horizon lies more universe, perhaps infinitely more, forever beyond our view. As you drift through this narrative, let the vast scales soothe you. The universe is so large that comprehending it requires releasing our everyday intuitions about space and distance. There's something deeply calming about cosmic immensity. It puts our daily concerns in perspective, reminds us of our place in something incomprehensibly vast and ancient. So settle in, take a deep breath, and prepare for the longest journey ever conceived. We're going to travel farther than light itself could travel in the universe's 13.8 billion year history. We're going to the edge of everything we can see and perhaps glimpse what lies beyond. Before we can journey to the edge, we must address a fundamental misconception. Where is the center of the universe from which we'll begin our journey? The surprising answer is that the universe has no center, or more accurately, every point in the universe is equally its center. This seems impossible. How can something not have a center? Everything we experience in daily life has a center. A ball has a center. A room has a center. Earth has a center. Surely the universe must have a center too, perhaps the point where the Big Bang occurred, the place from which everything exploded outward. But the Big Bang didn't happen at a point in space. It happened everywhere simultaneously. The Big Bang was not an explosion into empty space, but an expansion of space itself. Every point in the universe was, 13.8 billion years ago, compressed together into an infinitely small, infinitely dense state. When the universe began expanding, every point expanded away from every other point. There was no central explosion point. The explosion happened everywhere at once. Imagine the surface of a balloon being inflated. Draw dots on the balloon's surface to represent galaxies. As the balloon expands, every dot moves away from every other dot. From the perspective of any dot, all other dots are moving away from it. Every dot could claim to be the center of the expansion, and every dot would be equally correct or equally wrong. The balloon's surface has no center point on the surface itself. The balloon's center in three-dimensional space is irrelevant to the two-dimensional surface creatures living on it. Our universe is like that balloon's surface, But in 3 dimensions, space itself is expanding, carrying galaxies apart like dots on an inflating balloon. Every galaxy sees all other galaxies receding. Every point in space can claim to be the center, which means no point is special. The universe has no center, or equivalently, every point is the center. This has a profound implication for our journey. We cannot travel from the center to the edge because there is no center. We can only travel from here, wherever we happen to be outward in any direction, until we reach the limits of what we can observe. Our starting point, Earth, is no more or less central than any other point in the universe. So, let us begin here, on Earth, orbiting an ordinary star in an ordinary galaxy, at a location that is neither central nor peripheral, but simply one point among countless points in an infinite, or at least unimaginably vast cosmos. From here, we'll journey outward, watching the universe unfold in ever larger scales until we reach the cosmic horizon 46.5 billion light-years away. Our journey begins at home, Earth, a rocky planet orbiting the Sun at a distance of 150 million kilometers. This distance, one astronomical unit, is our first unit of cosmic measurement. Light takes 8 minutes and 20 seconds to travel from the Sun to Earth. When you see the Sun, you see it as it was 8 minutes ago. Let's accelerate away from Earth at many times the speed of light, an impossibility in real physics, but necessary for our journey. As we pull away, Earth shrinks to a blue marble, then a pale blue dot, then vanishes among the stars. The moon recedes. The sun's brilliance diminishes slightly as distance grows. Passing Mars's orbit, then the asteroid belt, we reach Jupiter at 5.2 AU from the Sunday. This giant world, 11 times Earth's diameter, dominates the outer solar system. Its gravity has shaped the architecture of planets, cleared zones in the asteroid belt, and protects the inner solar system from many comets. Jupiter takes 12 years to orbit the Sunday. From here, the Sun still looks bright but noticeably smaller than from Earth. Saturn at 9.5 AU, Uranus at 19 AU, Neptune at 30 AU, each marks another milestone in our outward journey. Neptune, the most distant planet, takes 165 years to complete one orbit. Beyond Neptune lies the Kuiper Belt, a disk of icy bodies extending to about 50 AU. Pluto, the most famous Kuiper Belt object, orbits at an average distance of 39 AU. Beyond the Kuiper Belt lies the scattered disk, then the Oort cloud, a spherical shell of trillions of comets surrounding the solar system from about 2,000 to 100,000 AU. The Oort cloud marks the gravitational edge of the Sun's influence. Beyond it, interstellar space begins. At 100,000 AU, we're 1.5 light-years from the Sunday. This is the distance light travels in 1.5 years. We've left kilometers and AU behind. Our unit is now the light year. The Sun is no longer the brightest star in the sky, just one star among many. The familiar constellations still look the same. We haven't traveled far enough to change them significantly. The nearest star, Proxima Centauri, lies 4 24 light-years away. We're approaching the middle of the vast emptiness between stars. Interstellar space is almost perfect vacuum, with densities of less than 1 atom per cubic centimeter. Temperatures hover just a few degrees above absolute zero, warmed only by starlight from distant suns and the faint cosmic microwave background radiation left over from the Big Bang. As we pass the midpoint between the Sun and Proxima Centauri, we cross an invisible boundary. The Sun is no longer our closest star. Proxima Centauri is. We've left the Sun's neighborhood and entered Proxima's. But Proxima is part of a triple star system, Alpha Centauri, and all three stars are part of the larger stellar neighborhood surrounding the Sunday. Proxima Centauri itself is a red dwarf, much smaller and cooler than the Sun, only about 12% of the Sun's mass and 14% of its diameter. It's so dim that despite being the closest star to Earth, it's invisible to the naked eye. Yet Proxima hosts at least 2 planets, including Proxima Centauri b, a rocky world in the star's habitable zone where liquid water might exist. This planet orbits in just 11 days, since Proxima's habitable zone is much closer than the Sun's due to the star's lower luminosity. The Alpha Centauri system is more complex. Alpha Centauri A and B are Sun-like stars orbiting each other every 80 years, their separation varying from 11 to 36 AU. Alpha Centauri A is slightly larger and brighter than the Sun. Alpha Centauri b is slightly smaller and dimmer. Proxima orbits this binary pair at about 13,000 AU, taking over 500,000 years to complete one orbit. Whether Proxima is gravitationally bound to the binary or just passing by is still debated. This local neighborhood contains about a dozen star systems within 10 light-years of the Sunday. Most are red dwarfs, small, dim, long-lived stars that are the most common type in the galaxy. Barnard's star, 6 light-years away, is another red dwarf, notable for its large, proper motion across the sky. Wolf, 359, Lalande 21185, Sirius and Lytton 726-8 are other neighbors, each with its own characteristics. There are also a few Sun-like stars, some white dwarfs, stellar corpses, and several brown dwarfs, failed stars, not quite massive enough to sustain fusion. This stellar density, about 1 star system per 300 cubic light-years, is typical of our region of the galaxy. Sirius, the brightest star in Earth's night sky, lies 8.6 light-years away. It's actually a binary system. Sirius A, a brilliant blue-white star twice the Sun's mass, orbited by Sirius B, a white dwarf, the collapsed core of a star that exhausted its fuel and shed its outer layers. Sirius B, though only Earth-sized, has about the Sun's mass, making it extraordinarily dense. A teaspoon of white dwarf material would weigh several tons on Earth. Interstellar space between these stars is not perfectly empty. Thin wisps of gas, mostly hydrogen, with some helium and trace heavier elements, drift between the stars at densities of perhaps 0.1 atoms per cubic centimeter. Interstellar dust, tiny grains of carbon and silicates, scatters starlight and creates dark clouds visible against the Milky Way's glow. Cosmic rays, high-energy particles accelerated by supernova shocks or other violent processes, permeate the interstellar medium, bombarding any material they encounter. The Sun, along with its neighbors, orbits the galactic center at about 220 kilometers per second. But the stars don't all move together. Each has its own orbital velocity, leading to relative motions of tens of kilometers per second. Stars pass by each other, their relative positions changing over thousands to millions of years. The constellations we see today are temporary configurations. In 100,000 years, they'll look completely different as stars drift to new positions. Passing 10 light-years from the Sun, we're now truly in interstellar space. The Sun has faded to a bright star, but no longer dominates the sky. Earth, Venus, Jupiter, all the planets are invisible, lost in the Sun's glare. Only from this distance do we truly appreciate the isolation of each star, separated from its neighbors by voids of dark space measured in light-years. Our journey has taken us from the scale of planets, measured in AU, to the scale of stellar neighborhoods, measured in light-years. We've traveled about 10 light-years, but the edge of the universe lies 46.5 billion light-years away. We've barely begun. We have 4.65 billion times farther to go. At 100 light-years from the Sun, the scale shifts again. We're no longer thinking about individual stars, but about regions of the galaxy, about stellar populations and galactic structures. Around us, thousands of stars populate the night sky, each separated from its neighbors by light-years of nearly empty space. The Sun lies in what's called the Orion Spur, a minor spiral arm of the Milky Way galaxy. We're about 26,000 light-years from the galactic center, roughly halfway between the center and the edge of the visible disk. This location, in the galaxy's suburbs, is fairly typical. Most stars in the Milky Way orbit at similar distances from the center. The Orion Spur is sometimes called the Orion Arm or local arm. It's not a major spiral arm, but a minor feature between two prominent arms, the Perseus arm on the outer side and the Sagittarius arm toward the galactic center. The spur is about 10,000 light-years long and 3,500 light-years wide, containing perhaps 100 million stars. The Sun orbits within this structure, taking about 230 million years to complete one galactic orbit, a galactic year or cosmic year. The spiral arms are regions of enhanced stellar density, particularly of young, massive stars. These arms aren't solid structures, but density waves, regions where material temporarily crowds together as it orbits. Think of them like traffic jams on a highway. Cars, stars, enter the jam, slow down, then leave, but the jam itself remains in roughly the same place. The spiral pattern rotates more slowly than the stars themselves orbit. Massive stars in the spiral arms live only millions of years before exploding as supernovae. Their short lifespans mean they don't have time to drift far from where they formed, so they trace out the spiral structure with their brilliant blue-white light. When we see images of spiral galaxies like M51 or M81, The prominent blue spiral arms are outlined by these young, massive stars. Between the arms lie older stellar populations, stars like the Sun and smaller, cooler red dwarfs. These stars formed long ago and have had time to drift away from their birthplaces, spreading throughout the disk. The interarm regions appear darker in visible light, but actually contain most of the disk's stars. They're just older and dimmer on average than the arm regions. The Milky Way's disk also contains vast molecular clouds, cold, dense regions of gas and dust where new stars form. The Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is the nearest large star-forming region, about 1,300 light-years away. Within these clouds, gravity pulls gas and dust together into clumps that collapse to form protostars, which eventually ignite fusion and become true stars. Stellar nurseries like Orion are messy, violent places. Newly formed massive stars blast their surroundings with intense ultraviolet light, ionizing nearby gas and creating glowing nebulae. Stellar winds, streams of charged particles flowing from the stars, push on surrounding material. When the most massive stars explode as supernovae, they inject enormous energy into their neighborhoods, compressing nearby gas and sometimes triggering new rounds of star formation while dispersing other clouds. As we travel outward from the Sun, we pass through the local stellar neighborhood into denser star fields. At 1,000 light-years, we can see the structure of the Orion spur taking shape, a slight enhancement in stellar density compared to the regions between spiral arms. The spur contains young, hot, blue stars, massive stars that live fast and die young in supernova explosions. These stars trace out the spiral structure, marking regions where gas has recently collapsed to form new stars. Red giant stars dot the landscape, elderly stars that have exhausted their core hydrogen and swollen to enormous sizes. Some are large enough to swallow Earth's orbit. White dwarfs, the exposed cores of dead, sun-like stars, contribute to the stellar population, though they're too dim to see from great distances. Neutron stars and black holes lurk invisibly, detectable only through their gravitational effects on visible companions. At 10,000 light-years, we're beginning to see the Milky Way's structure from outside our immediate neighborhood. Looking back toward the Sun, we can see the general plane of the galactic disk, a flattened distribution of stars, gas, and dust extending thousands of light-years in all directions, but only hundreds of light-years thick. The Milky Way is a disk galaxy, and we're traveling perpendicular to that disk, heading out of the plane. Glancing toward the galactic center, we see a brightening in stellar density. The center of the galaxy contains a bulge of old stars, denser than the disk. Hidden within that bulge, at the very center, lies Sagittarius A times a supermassive black hole with a mass of about 4 million suns. We can't see it directly, but we can observe stars orbiting it at tremendous speeds, their orbits revealing the black hole's enormous mass. At 26,000 light-years, we're as far from the Sun as the Sun is from the galactic center. Looking back at the Milky Way's disk, we see it edge on, if we look in one direction, face on if we look toward the galactic center. The disk contains 200 to 400 billion stars, most concentrated in a few spiral arms that wind around the center. Our Sun, invisible among so many, orbits the center once every 230 million years, a galactic year. Continuing outward, we leave the main disk behind. At 50,000 light-years, we're in the Milky Way's halo, a roughly spherical region surrounding the disk, sparsely populated with ancient stars and globular clusters. Globular clusters are tight spheres of hundreds of thousands of old stars, gravitationally bound, orbiting the galaxy like moons orbit a planet. The Milky Way has about 150 known globular clusters, each a remnant from the galaxy's early formation. The halo also contains dark matter, mysterious invisible matter that makes up about 85% of the galaxy's mass. We can't see dark matter, but we can infer its presence from its gravitational effects. Stars in the outer disk orbit faster than they should based on visible matter alone. Dark matter's additional gravity explains the extra speed. The dark matter forms a massive halo, extending far beyond the visible stars, perhaps 600,000 light-years from the galactic center. At 100,000 light-years from the Sun, about 75,000 light-years from the galactic center, we've left the Milky Way's visible disk behind. Looking back, we see our galaxy as an outside observer would, a beautiful spiral with multiple arms, a central bulge of yellowish old stars, and a disk of blue-white young stars. If we could see in other wavelengths, we'd see vast clouds of hydrogen gas, regions of star formation glowing pink with ionized gas, and dark dust lanes obscuring parts of the disk. But we're not done with the Milky Way yet. The dark matter halo extends much farther, and orbiting within it are dozens of satellite galaxies, small galaxies gravitationally bound to the Milky Way, orbiting it much as the Moon orbits Earth. The most famous are the large and small Magellanic Clouds, visible from Earth's southern hemisphere as fuzzy patches of light. These dwarf galaxies orbit the Milky Way, eventually to be absorbed into the larger galaxy over billions of years. At 300,000 light-years, we've reached the edge of the Milky Way's gravitational influence. Beyond this lies intergalactic space, the void between galaxies. The Milky Way, our cosmic home, is behind us. We've traveled 300,000 light-years, but the edge of the observable universe remains 46.5 billion light-years away. We have 155,000 times farther to go. Crossing into intergalactic space, we enter a realm of emptiness that dwarfs even the voids between stars. Galaxies are separated by millions of light-years distances so vast that even traveling at the speed of light would take eons to cross them. The Milky Way is not alone in space. It's part of a small cluster of galaxies called the Local Group, containing about 80 known galaxies within a region about 10 million light-years across. Most are dwarf galaxies, small galaxies containing millions to billions of stars, compared to the hundreds of billions in the Milky Way. But the Local Group also contains three large galaxies: the Milky Way, Andromeda, M31, and Triangulum, M33. At 500,000 light-years from the Milky Way, we're midway to Andromeda. The space between galaxies is not perfectly empty. It contains thin wisps of gas, the occasional rogue star ejected from its home galaxy, and vast quantities of dark matter. But the density is extraordinarily low, less than 1 atom per cubic meter. This intergalactic medium is so diffuse that it's better vacuum than anything we can create in laboratories on Earth. Andromeda Galaxy lies 2.5 million light-years from the Milky Way. It's the most distant object visible to the naked eye from Earth, a faint smudge of light that, through telescopes, resolves into a magnificent spiral galaxy larger than the Milky Way. Andromeda contains about 1 trillion stars, perhaps twice as many as the Milky Way. Like our galaxy, it has spiral arms, a central bulge, and a supermassive black hole. At its core, this one about 100 to 200 million solar masses, significantly larger than the Milky Way's 4 million solar mass black hole. Andromeda's structure reveals a violent history. Its core appears double, suggesting it consumed another galaxy in a collision perhaps 2 billion years ago. The devoured galaxy's core sank to Andromeda's center but hasn't fully merged, creating the observed double structure. This kind of galactic cannibalism is common throughout the universe. Large galaxies grow by consuming smaller ones. Observations show Andromeda is surrounded by a vast halo of ancient stars and numerous satellite dwarf galaxies. At least 25 satellite galaxies have been confirmed, with many more likely awaiting discovery. These satellites orbit Andromeda much as the Magellanic Clouds orbit the Milky Way. Some satellites show signs of being tidally disrupted by Andromeda's gravity, their stars stripped away in long stellar streams. Andromeda and the Milky Way are approaching each other at about 110 kilometers per second. In about 4.5 billion years, they will collide and merge, forming a giant elliptical galaxy that astronomers have nicknamed Milkomeda. This collision will radically reshape both galaxies, but ironically, individual stars are unlikely to collide. The distances between stars are so vast that they'll pass through each other like 2 swarms of gnats interpenetrating. The real drama will be in the gas clouds, which will collide, compress, and trigger tremendous bursts of star formation. Computer simulations of the Milky Way-Andromeda collision show a complex dance lasting several billion years. The galaxies will make a close pass, swing apart, then fall back together for another pass. With each passage, tidal forces will pull long streamers of stars from both galaxies, creating spectacular structures. Eventually, the galaxies will merge completely, their stars mixing, their supermassive black holes spiraling together and merging into an even larger black hole. The resulting elliptical galaxy will gradually settle into a stable configuration, all traces of the original spiral structures erased. The Sun and Earth will survive this collision. By then, the Sun will be nearing the end of its main sequence lifetime, having expanded somewhat and become hotter, potentially making Earth uninhabitable even before the galactic merger. During the collision, Earth's sky will be spectacular. Andromeda will fill a large portion of the sky during close passes, and the burst of star formation will create brilliant clusters of young stars. But Earth itself will likely remain in a stable orbit, merely exchanging the Sun's current position in the Milky Way for a new position in Milkomeda. Passing Andromeda at 2.5 million light-years from the Milky Way, we observe its structure. It's tilted relative to us, showing its disk at an angle. We can see dark dust lanes silhouetted against the bright disk, blue regions of active star formation, and the yellowish glow of the central bulge. Andromeda has its own satellite galaxies, small dwarf galaxies orbiting it just as the Magellanic Clouds orbit the Milky Way. Triangulum Galaxy M33 lies about 3 million light-years from the Milky Way, making it the third largest galaxy in the local group. It's a smaller spiral with about 40 billion stars, still enormous by absolute standards, but modest compared to Andromeda and the Milky Way. Triangulum may be a satellite of Andromeda, or may be an independent member of the local group. Its precise relationship to the larger galaxies is still debated. The other members of the local group are mostly dwarf galaxies with evocative names: the Fornax dwarf, the Sculptor dwarf, Leo I, and Leo the Sexton's dwarf, and dozens more. Each contains millions to a few billion stars, small by galactic standards. Many are irregular in shape, lacking the symmetric spiral or elliptical forms of larger galaxies. Some are being torn apart by the gravitational tides of the Milky Way or Andromeda, their stars gradually absorbed into the larger galaxies. The local group is gravitationally bound. All its galaxies orbit a common center of mass, held together by their mutual gravity and the gravity of dark matter pervading the group. Over billions of years, many of these galaxies will merge, gradually building up the largest galaxies while consuming the smaller ones. This process of hierarchical assembly has shaped galaxies throughout cosmic history. At 10 million light-years from the Milky Way, we've crossed the local group and reached its edge. Looking back, we can see the local group as a small cluster of galaxies, the Milky Way and Andromeda dominating, smaller galaxies scattered around them. It's one small knot of matter in the vast cosmic web. But the local group is just one small cluster. Beyond it lies a much larger structure, the Virgo supercluster, of which the local group is a minor outlying member. We've traveled 10 million light-years. The edge of the universe remains 46.5 billion light-years away. We have 4,650 times farther to go. Beyond the local group, the universe's large-scale structure becomes apparent. Galaxies are not randomly distributed, but form patterns, clusters, superclusters, filaments, and walls with vast empty voids between them. This structure, called the cosmic web, is the largest known structure in the universe. At 20 million light-years, we're approaching the Virgo cluster, the nearest large cluster of galaxies. The Virgo cluster contains over 1,500 galaxies within a region about 15 million light-years across. At its heart lies M87, a giant elliptical galaxy containing several trillion stars. M87 hosts a supermassive black hole with a mass of 6.5 billion suns, the first black hole ever directly imaged, photographed in 2019 by the Event Horizon Telescope. The Virgo cluster is the gravitational center of the Virgo supercluster, a vast structure containing tens of thousands of galaxies spread across 110 million light-years. The local group is on the outskirts of this supercluster, being pulled toward Virgo by its gravitational attraction. Our entire local group is moving at about 600 kilometers per second toward the Virgo cluster, falling into its gravitational well. But recent discoveries have revealed an even larger structure. In 2014, astronomers mapped the motions of galaxies in our cosmic neighborhood and discovered that the Virgo supercluster is itself part of a still larger structure, Laniakea, Hawaiian for immense heaven. The Laniakea supercluster contains about 100,000 galaxies spread across 520 million light-years. It's defined not by proximity alone, but by shared motion. All galaxies in Laniakea are flowing toward a common gravitational center called the Great Attractor. The Great Attractor is a gravitational anomaly in the direction of the Hydra and Centaurus constellations, about 250 million light-years away. It's not a single object, but a massive concentration of mass multiple galaxy clusters and dark matter that exerts enormous gravitational pull on surrounding galaxies. Our local group, the Virgo cluster, and thousands of other galaxies are all streaming toward the Great Attractor at hundreds of kilometers per second. As we travel through Laniakea, we pass countless galaxy clusters. Each cluster contains hundreds to thousands of galaxies, bound together by gravity, swimming in vast halos of dark matter and hot gas. The intra-cluster medium gas between the galaxies is heated to tens of millions of degrees by the gravitational energy of galaxy motions, glowing in X-rays. At 100 million light-years from the Milky Way, we can see the large-scale structure clearly. Galaxies are arranged in sheets and filaments, like soap bubbles or foam, with enormous voids between them. These voids, regions of space containing very few galaxies, can be hundreds of millions of light-years across. The largest known void, the Boötes void, is 330 million light-years in diameter and contains only about 60 galaxies in a volume that would typically contain 2,000. The cosmic web structure arose from tiny density fluctuations in the early universe. Regions slightly denser than average had slightly stronger gravity, attracting more matter, growing denser still. Over billions of years, this gravitational instability amplified microscopic variations into the vast structures we see today. Dark matter played a crucial role. It clumped together gravitationally without being dispersed by radiation pressure, providing the gravitational scaffolding on which galaxies and galaxy clusters formed. At 250 million light-years, we pass through the Great Attractor region. From this vantage, we can see it's not a single point, but a complex structure. The Norma cluster, the Centaurus supercluster, and other massive galaxy concentrations. Beyond the Great Attractor lies the Shapley supercluster, an even more massive structure 650 million light-years away, containing 8,000 galaxies. The Shapley supercluster, in turn, is pulling on the Great Attractor, which is pulling on us. The universe is a hierarchy of gravitational attractions, each structure influenced by larger structures beyond it. At 500 million light-years from the Milky Way, we've crossed Laniakea and reached its boundary. Looking back, we can see the full extent of our home supercluster, a vast cosmic river of galaxies, all flowing toward common centers of mass, all interconnected by invisible dark matter filaments. Laniakea is our cosmic address at the largest scales: Earth, Solar System, Orion Spur, Milky Way, Local Group, Virgo Supercluster, Laniakea. But Laniakea is just one supercluster among thousands. The universe contains structure at even larger scales. We've traveled 500 million light-years. The edge of the observable universe remains 46.5 billion light-years away. We have 93 times farther to go. At 1 billion light-years from the Milky Way, we've traveled so far that light from here took 1 billion years to reach Earth. We're seeing the universe not as it is today, but as it was 1 billion years ago, when life on Earth was just multicellular organisms in the oceans before plants had colonized land. From this distance, individual galaxies blur together. We see only the large-scale structure, filaments of galaxies stretching across hundreds of millions of light-years, sheets where filaments intersect, and vast voids nearly empty of galaxies. The cosmic web, clearly visible now, looks organic, like neural networks or blood vessels, patterns that emerge whenever matter self-organizes under the influence of attractive forces. The largest structures in the universe are apparent at these scales. The Sloan Great Wall, discovered in 2003, is a vast sheet of galaxies 1.38 billion light-years long. The Hercules Corona Borealis Great Wall, possibly even larger at 10 billion light-years, is so vast that it challenges our understanding of how structure formed. It seems almost too large to have arisen from gravitational collapse in the universe's finite age. Galaxy clusters within these structures often show signs of violent interactions. Clusters collide with each other at speeds of thousands of kilometers per second, merging over millions of years. These collisions heat gas to extreme temperatures, produce shock waves, and trigger bursts of star formation as gas clouds compress. The Bullet Cluster, two colliding galaxy clusters about 3.7 billion light-years away, famously provided strong evidence for dark matter. The visible gas collided and slowed down. But the dark matter detected through gravitational lensing passed through without interacting, proving that most mass in the cluster was invisible dark matter, not gas. At 5 billion light-years, we're looking back 5 billion years in time. We see the universe as it was when the Sun and Earth were forming from a collapsing cloud of gas and dust. The galaxies here look younger, bluer on average, with more active star formation, more irregular shapes. The universe has been evolving. Galaxies in the distant past were smaller, more chaotic, with higher rates of star formation and galaxy mergers. Quasars become more common at these distances. Quasars are the blazingly bright cores of galaxies powered by supermassive black holes actively consuming matter. As material falls into the black hole, it heats up and emits enormous amounts of energy. A single quasar can outshine an entire galaxy of stars. Quasars were much more common in the universe's youth, when galaxy collisions and mergers were more frequent, funneling gas towards central black holes. At 10 billion light-years, we're seeing the universe as it was 10 billion years ago, only 3.8 billion years after the Big Bang. This is the era of peak star formation in cosmic history. More stars were being born per year than at any time before or since. Galaxies were gas-rich, colliding frequently, experiencing vigorous star formation. The universe was brighter and more active than it is today. The Hubble Deep Field and Hubble Ultra Deep Field images, showing small patches of sky in extreme detail, reveal thousands of galaxies at these distances. Each galaxy appears as it was billions of years ago. Some are familiar spirals and ellipticals. Others are irregular, distorted by collisions, or simply smaller building blocks that will merge to form larger galaxies. We're seeing galaxies in their youth, still growing, still actively forming stars. The cosmic web's structure is still visible at 10 billion light-years, but it's less pronounced than in the nearby universe. Structures have had less time to grow. The universe was denser, with galaxies closer together on average. The expansion of space was slower then, held back by the gravitational attraction of matter. Only in the past 5 billion years has the expansion begun accelerating, driven by dark energy. At 13 billion light-years, we're seeing the universe just 800 million years after the Big Bang. This is near the end of the cosmic dark ages, the period after the Big Bang cooled enough for neutral hydrogen to form, but before the first stars ignited to reionize it. The first galaxies are forming here, small and irregular, nothing like the grand spirals and ellipticals of the present-day universe. These early galaxies are small because structure forms hierarchically. Small structures form first, then merge to build larger ones. The galaxies we see at 13 billion light-years are the ancestors of present-day galaxies, destined to collide and merge many times before reaching the forms we see in the nearby universe. A galaxy that formed 800 million years after the Big Bang might have merged with 10, 20, or 100 other galaxies by the present day, each merger adding stars and mass. The first stars, population 3 stars, were fundamentally different from stars today. They formed from primordial gas consisting only of hydrogen, helium, and trace amounts of lithium created in the Big Bang. No heavy elements existed yet. Those would be forged in the cores of stars and dispersed by supernovae. Without heavy elements, which help cool collapsing gas clouds, the first stars had to form from much larger gas masses, making them extraordinarily massive, perhaps 100 to 1,000 times the Sun's mass. These monster stars burned brilliantly but briefly, exhausting their fuel in just a few million years before exploding as supernovae. These explosions scattered the first heavy elements, carbon, oxygen, iron, and others into the surrounding gas. Subsequent generations of stars incorporated these elements, and each generation enriched the cosmos further. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were forged in stars that lived and died over billions of years, their deaths seeding space with the raw materials for planets and life. The epoch of reionization occurred between about 400 million and 1 billion years after the Big Bang. During this period, the first stars and galaxies emitted enough ultraviolet radiation to reionize the hydrogen-filling space, tearing electrons from neutral atoms and making the universe transparent to ultraviolet light once again. This transition marked the end of the cosmic dark ages and the beginning of the universe as we know it, filled with shining galaxies rather than dark hydrogen clouds. The James Webb Space Telescope, launched in 2021, has pushed our view back even farther, detecting galaxies that formed just 200 to 300 million years after the Big Bang. These galaxies are surprisingly bright and massive for their age, challenging models of how quickly galaxies can form. Some contain hundreds of millions of solar masses of stars despite forming when the universe was barely 2% of its current age. Understanding how galaxies grew so quickly requires refining our models of star formation and dark matter dynamics in the early universe. JWST has also detected the chemical signatures of early galaxies, revealing that star formation and metal enrichment happened faster than expected. Some galaxies show evidence of multiple generations of stars within their first few 100 million years, meaning the cycle of star birth, death, and rebirth occurred rapidly. The early universe was apparently more efficient at forming stars than our models predicted. At 13.5 billion light-years, galaxies become scarce. We're approaching the epoch of reionization, when the first stars and galaxies formed and their ultraviolet light reionized the hydrogen-filling space. Before this, the universe was dark, filled with neutral hydrogen that absorbed ultraviolet light, preventing us from seeing earlier epochs directly with optical telescopes. We've traveled 13.5 billion light-years, looking back 13.5 billion years in time. We're approaching the edge of what optical telescopes can see. Beyond lies a final frontier, the cosmic microwave background, the oldest light in the universe. We're getting close to the edge, but we still have distance to cover. The observable universe extends to 46.5 billion light-years. We have 33 billion light-years to go. At 13.7 billion light-years, we're seeing the universe just 100 million years after the Big Bang. Galaxies here are rare, small, primitive. Star formation has barely begun. The universe is transitioning from dark ages to the light of the first stars. But we cannot see much farther back with optical telescopes. At about 13.8 billion years after the Big Bang, corresponding to what we see at about 45 billion light-years due to expansion, we reach a barrier, the surface of last scattering, the source of the cosmic microwave background radiation. To understand this surface, we must understand the early universe's history. In the beginning, the universe was extremely hot and dense, too hot for atoms to form. Matter existed as a plasma of protons, electrons, and photons, all interacting intensely. Photons, light particles, could not travel far before scattering off an electron, like trying to see through fog. The universe was opaque. As the universe expanded, it cooled. About 380,000 years after the Big Bang, when the universe was about 3,000 degrees Kelvin, cool enough for protons and electrons to combine into neutral hydrogen atoms, the fog cleared. With no free electrons to scatter off, photons could suddenly travel freely. The universe became transparent. The light released at that moment, the first light to travel unimpeded through space, is what we detect today as the cosmic microwave background, CMB. The surface of last scattering is the spherical shell around us from which the CMB originated. It's not a physical surface, but a moment in time, the moment when the universe became transparent, occurring everywhere simultaneously. We see it as a surface because we see it from our position in space and time. Observers anywhere else would see their own surface of last scattering centered on them. Because the universe has expanded since that light was emitted, the surface of last scattering is now about 46 billion light-years away. The light itself took only 13.8 billion years to reach us, but the space between us and the emission point has stretched during that time, making the current distance much greater. The CMB is the oldest light in the universe, and it comes from every direction. With microwave telescopes, we can map the temperature of this ancient light across the entire sky. It's remarkably uniform, about 2.725 Kelvin everywhere, but with tiny variations, about 1 part in 100,000. These tiny fluctuations, called anisotropies, are the seeds of all structure in the universe. The slightly denser regions visible in the CMB correspond to slight overdensities in the early universe. These overdensities had slightly stronger gravity, attracting more matter, growing over billions of years into the galaxies, clusters, and superclusters we see today. The pattern of fluctuations in the CMB tells us about the composition of the universe, the geometry of space, and the nature of the Big Bang itself. The CMB has been mapped in exquisite detail by satellites like COBE, WMAP, and Planck. These maps show us the universe as it was 380,000 years after the Big Bang, a baby universe, smooth and simple, just beginning to develop structure. It's the oldest photograph of the cosmos, a snapshot from before galaxies, before stars, before anything complex existed. Standing at the surface of last scattering, we've reached the edge of light. We cannot see farther with electromagnetic radiation because before this moment, the universe was opaque. Any photons from earlier times were scattered countless times and thermalized. They lost all information about their origin, contributing only to the uniform glow of the CMB. This is the edge of the visible universe in a very real sense. Beyond this lies the universe before 380,000 years after the Big Bang, a time we cannot observe with light. But cannot observe with light doesn't mean cannot observe at all, or doesn't exist. Two other messengers can potentially let us see earlier: gravitational waves and neutrinos. Both can propagate through the opaque early universe. Gravitational wave detectors might someday detect primordial gravitational waves from the Big Bang itself, and neutrino telescopes might detect the cosmic neutrino background, released when the universe was just 1 second old. These observations would push the edge of what we can see even farther back in time. But for now, with electromagnetic radiation light, the surface of last scattering is the edge. We've traveled as far back in time as light allows. We're looking at the universe 380,000 years after its beginning, seeing the moment when light first traveled freely through space. Yet this is not the edge of the universe itself, it's only the edge of what we can see. The universe extends beyond the surface of last scattering, both in space and in time. Space existed before this moment, and it extends farther than we can see. We've reached the edge of the observable universe, but not the edge of the universe itself. At 46.5 billion light-years from our starting point, we've reached the edge of the observable universe, the cosmic horizon. This is as far as light has been able to travel in the 13.8 billion years since the Big Bang, accounting for the expansion of space during that time. Beyond this horizon lies more universe, but it's forever beyond our observation. This horizon is not a physical boundary where space ends. It's an observational limit created by the finite age of the universe and the finite speed of light. Light from regions beyond 46.5 billion light-years hasn't had time to reach us yet. As the universe ages, the observable universe grows, revealing regions previously beyond our horizon, but the expansion of space ensures that some regions will remain forever beyond reach. What lies beyond the horizon? In all likelihood, more of the same. Galaxies, galaxy clusters, cosmic web structure, continuing indefinitely. There's no reason to think the universe suddenly changes character at the edge of what we can see. The laws of physics are the same everywhere. The cosmic microwave background looks the same in all directions. The large-scale structure we observe shows no preference for any direction. All evidence suggests the universe is homogeneous and isotropic, at large scales the same everywhere and in all directions. If the universe is infinite in extent, as many cosmological models suggest, then beyond our observable patch lie an infinite number of galaxies, an infinite number of stars, an infinite expanse of space. Our observable universe, vast as it is, would be an infinitesimal fraction of the whole, like a single drop in an infinite ocean. Alternatively, the universe might be finite but unbounded, wrapped back on itself like the surface of a sphere. Just as you can travel around Earth's surface forever without reaching an edge, you might be able to travel through a finite universe forever without reaching a boundary. Such a universe would have no edge, no center, but finite volume. Current observations suggest the universe is very close to spatially flat, Euclidean, which is consistent with either infinite extent or a finite but very large wraparound. So large that the curvature is imperceptible within our observable universe. Some physicists speculate about even stranger possibilities. Eternal inflation theory suggests our observable universe is just one bubble in a vast, eternally inflating multiverse. In this picture, inflation, the exponential expansion that occurred in the universe's first fraction of a second, never completely ended. It continues in most of space, with occasional regions like ours transitioning out of inflation to form pocket universes. Each pocket universe might have different physical constants, different particles, different laws of physics, determined by how quantum fields settled during the transition. If eternal inflation is correct, then beyond our cosmic horizon lies not just more of our universe, but potentially an infinite number of other universes, each with its own properties, most of them wildly different from ours. This multiverse would be forever beyond observation. No signal from another pocket universe could reach us across the inflating space between, but it would exist nonetheless, a consequence of the same physics that shaped our own universe. Other multiverse proposals exist, the many worlds interpretation of quantum mechanics, which suggests every quantum measurement splits the universe into branches, the mathematical universe hypothesis, which proposes that every mathematically consistent structure exists as a physical universe, the landscape of string theory, offering perhaps 500 different possible vacuum states, each potentially realized somewhere in a vast multiverse. All these ideas are speculative, extending beyond what we can observe or test experimentally. They arise from attempts to explain fine-tuning why the laws of physics and constants of nature in our universe seem precisely calibrated to allow complexity and life. In a multiverse with varying physical laws, we would inevitably find ourselves in a universe compatible with our existence, making the apparent fine-tuning unsurprising. But returning from speculation to observation, we know with confidence that the universe extends beyond our cosmic horizon. We see the CMB from 46.5 billion light-years away in all directions. The universe that emitted that radiation extends beyond it. There's no reason it would stop at precisely the distance visible to us. Light from farther regions simply hasn't reached us yet. As time passes, our observable universe grows. Light from slightly more distant regions reaches us, expanding our horizon by about 1 light-year per year, accounting for expansion. But the universe's expansion is accelerating, driven by dark energy. Regions currently beyond our horizon are receding from us, faster than light can travel through expanding space. Most of the universe beyond our current horizon will remain forever beyond it, the accelerating expansion ensuring we'll never see light from them, no matter how long we wait. The edge of the observable universe is thus a one-way membrane. We can see light that was emitted long ago from regions now 46.5 billion light-years away. But light we emit now will never reach most of those regions by the time our light has traveled 46.5 billion light-years. Those regions will have receded much farther, carried away by accelerating expansion. The future of observation is sobering. Distant galaxies will gradually disappear from our view as they cross our cosmic event horizon, receding forever beyond reach. In the far future, trillions of years from now, the only galaxies visible will be those gravitationally bound to us, the merged remnants of the local group. All other galaxies will have receded beyond our cosmic horizon, unreachable and unobservable. Future astronomers, if any exist, would observe a universe that appears to contain only one galaxy, unless they have preserved records from our era documenting the existence of billions of galaxies once observable. This is the ultimate edge, not a boundary where space ends, but a horizon beyond which observation becomes impossible. It's an edge created not by space, but by time and expansion, by the speed of light and the acceleration of cosmic expansion. Beyond this edge lies more universe, perhaps infinitely more, forever beyond our sight. Having reached the edge of the observable universe, let us contemplate what this edge means for the universe's geometry, extent, and ultimate fate. These questions, among the deepest in cosmology, relate directly to the nature of the edge we've reached. The shape of space itself determines whether the universe is finite or infinite, whether it has edges or wraps back on itself. General relativity tells us that space can be curved by matter and energy. At small scales, near massive objects like stars and black holes, this curvature is obvious. It's what we call gravity. But the universe as a whole can also have a global curvature, determined by its average density of matter and energy. There are three possibilities for the universe's global geometry. Positive curvature, closed universe. Like the surface of a sphere, space curves back on itself. If you traveled far enough in a straight line, you'd eventually return to your starting point. Such a universe would be finite in volume but have no edge or boundary, just as the surface of a sphere is finite but has no edge. The universe would eventually stop expanding and recollapse in a big crunch. Negative curvature, open universe. Like the surface of a saddle, space curves away from itself. This universe would be infinite in extent, expanding forever. Parallel lines diverge. The angles of a triangle sum to less than 180 degrees. Zero curvature, flat universe. Space is Euclidean, following the geometry we learn in school. Parallel lines remain parallel. Triangles have angles summing to 180 degrees. A flat universe could be infinite, extending forever, or finite, but unbounded, wrapping around like a torus, depending on its topology. A flat universe would expand forever, gradually slowing but never stopping. Observations of the cosmic microwave background by satellites like WMAP and Planck have measured the universe's curvature with exquisite precision. The result? The universe is flat, or extraordinarily close to flat, within 0.4% of perfect flatness. This suggests the universe is either exactly flat, infinite, or so close to flat that any curvature is undetectable within our observable patch. A flat universe can be infinite, extending forever in all directions. If so, then our cosmic horizon at 46.5 billion light-years is not approaching any edge. There is no edge to approach. Beyond our horizon lies infinite space with infinite galaxies, forever beyond our view, but nonetheless real. The universe's fate depends on its content. For decades, cosmologists thought matter dominated the universe. If matter density exceeded a critical value, gravity would eventually halt expansion and cause recollapse, Big Crunch. If matter density was below critical, expansion would continue forever, gradually slowing but never stopping. Then, in 1998, observations of distant supernovae revealed something shocking. The universe's expansion is accelerating. Instead of slowing down, as matter's gravity should cause, the expansion is speeding up. This implies the existence of dark energy, a mysterious form of energy with negative pressure that pushes space apart rather than pulling it together. Dark energy makes up about 68% of the universe's total energy. Dark matter accounts for 27%. Ordinary matter, the stuff of stars, planets, and people, is just 5%. The universe is dominated by components we barely understand. Dark energy's nature remains one of physics' greatest mysteries. It might be Einstein's cosmological constant, representing the energy of empty space itself. Or it might be a dynamic field that changes over time. Depending on dark energy's nature, the universe's fate could be Big Freeze. If dark energy is a cosmological constant, expansion accelerates forever. Galaxies recede beyond cosmic horizons. Stars exhaust their fuel and die. Eventually, even protons decay, if they do, leaving a cold, dark, dilute sea of photons and black holes. After 100 years, even black holes evaporate through Hawking radiation, leaving literally nothing but faint radiation in eternal darkness. Big Rip. If dark energy strengthens over time, expansion accelerates catastrophically. Eventually, expansion becomes so violent that it tears apart galaxies, then solar systems, then planets, then atoms, then even subatomic particles. The universe ends in a cataclysm where the fabric of space itself is torn apart. Big Crunch. If dark energy somehow weakens or reverses, gravity might eventually overcome expansion, causing the universe to recollapse, ending in a hot, dense singularity like the Big Bang but in reverse. Current observations favor a cosmological constant, suggesting a Big Freeze fate, eternal expansion into cold darkness. But dark energy's nature is uncertain, and its behavior over trillions of years is unknown. The universe's ultimate fate remains an open question. For our journey to the edge, these considerations tell us that the edge at 46.5 billion light-years is not fundamental. It's a horizon created by observation limits, not a boundary of space itself. Space probably extends far beyond, perhaps infinitely. The true extent of the universe is unknown and perhaps unknowable. But it's almost certainly far larger than our observable patch. The edge we've reached is an edge of knowledge, not an edge of existence. It's a frontier beyond which direct observation fails, but beyond which the universe continues. It's simultaneously the farthest we can see and a reminder of how much we cannot see, a humbling perspective on our place in the cosmos. We've journeyed 46.5 billion light-years from Earth, reaching the edge of the observable universe. We've seen galaxies, clusters, superclusters, the cosmic web, and finally the ancient light of the cosmic microwave background. We've reached the frontier of what is observable. But we've also reached a deeper frontier, the limit of what we can know through direct observation. This edge raises profound philosophical questions. If the universe extends beyond what we can observe, if regions exist from which light will never reach us, in what sense can we say we know about them? Science is built on empirical observation, on testing theories against evidence. What does science say about regions forever beyond observation. One response is that we can infer what lies beyond our horizon. The universe appears homogeneous and isotropic, the same in all directions. The CMB is uniform. The distribution of galaxies shows no preferred direction. The laws of physics work the same everywhere we've tested them. It would be extraordinary if the universe suddenly changed character precisely at the edge of what we can see. The simplest assumption, the Copernican principle extended to its logical conclusion, is that our observable universe is typical, that more of the same lies beyond. But this is an assumption, not an observation. We're extrapolating beyond our data. This extrapolation is reasonable, supported by all observations, consistent with theory, but it's not directly testable. We're in the realm of inference and philosophy, not pure empiricism. Eternal inflation and multiverse theories push this even further. They postulate regions with different laws of physics, forever beyond our observation. Are such theories scientific? They make predictions about what we should observe in our observable universe, which is testable, but their claims about unobservable regions cannot be tested directly. Some philosophers of science argue this makes them metaphysics, not physics. Yet dismissing such theories seems premature. The history of science is filled with initially unobservable entities, atoms, black holes, other galaxies that were later confirmed. What's unobservable today might become observable tomorrow with better technology. And even if some regions are forever beyond direct observation, their existence might have indirect consequences we can detect. The edge of the observable universe also relates to fundamental limits in physics. Quantum mechanics and general relativity are two great theories. Both suggest there are limits to what can be known. The Heisenberg uncertainty principle limits how precisely we can simultaneously know certain pairs of properties. Black hole event horizons create regions forever beyond observation from outside. Perhaps cosmic horizons are another example of fundamental limits imposed by the structure of reality itself. There's something both frustrating and beautiful about these limits. Frustrating because we want complete knowledge, perfect understanding. Beautiful because they remind us that the universe is grander than our comprehension, that mystery remains even at the frontiers of science. For most of human history, the edge of the known world was merely a function of how far travelers had explored. As exploration progressed, the edge receded. The age of exploration revealed that Earth has no edge. It's a sphere, finite but unbounded. Now, exploring the cosmos, we've discovered that the universe may be similar. No edge in space, but an observational edge imposed by the speed of light and the finite age of the universe. This edge is, in a sense, more fundamental than the edges known to ancient explorers. We cannot explore beyond it, no matter how advanced our technology becomes. It's created by the structure of space-time itself, by causality, by the fact that information cannot travel faster than light. It's an edge written into the laws of physics. Yet even this edge is not static. As the universe ages, our observable universe grows. Light from slightly more distant regions reaches us, expanding our horizon. What is beyond the edge today might be observable tomorrow. The edge of knowledge recedes, just as it always has in human history, though ultimately, accelerating expansion means some regions currently observable will eventually recede beyond our future horizon. Contemplating this edge teaches humility. The observable universe contains perhaps 100 billion galaxies, each with hundreds of billions of stars spanning 93 billion light-years. It's almost incomprehensibly vast. Yet it might be an infinitesimal fraction of the whole universe, like a single atom in Earth's oceans. Most of reality might be forever beyond our observation. This perspective puts human concerns in context. Our planet is a pale blue dot orbiting an ordinary star in a galaxy among billions. Our entire observable universe might be a tiny patch of something far larger. Our lives, our civilizations, our species, all are brief flickers in cosmic time, localized in an infinitesimal region of space. Yet, this perspective also elevates human achievement. Despite being such tiny beings in such a vast cosmos, we've managed to observe and understand our universe at the largest scales. We've measured the universe's age, mapped its structure, traced its history back to fractions of a second after the Big Bang. We've reached the edge of the observable universe with thought and observation, if not with physical travel. For creatures whose ancestors were fish, this is an extraordinary accomplishment. The edge of the universe is ultimately the edge of human knowledge encountering the structure of reality. It's where what we can know meets what we cannot know, where observation fails and inference begins, where science approaches philosophy. It's a frontier that challenges us to think carefully about the limits of knowledge while celebrating how far knowledge has taken us. Our journey has taken us from Earth to the edge of the observable universe, 5 billion light-years away. We've crossed the solar system in seconds, the galaxy in minutes, the local group in hours, the cosmic web over days, finally reaching the ancient light of the cosmic microwave background after a journey through all of space and time. We've learned that the universe has no center, or that every point is equally its center. We've seen that edge can mean many things. The edge of the observable universe at 46.5 billion light-years, the surface of last scattering where the CMB originated, the cosmic horizon beyond which we cannot see. We've contemplated what lies beyond, more universe, perhaps infinitely more, forever beyond our observation. Now, let us return home. The journey back is instantaneous. We simply turn our perspective around. Suddenly, we're looking back toward the Milky Way from the cosmic horizon, seeing our galaxy as it was 13.8 billion years ago, not yet formed, just density fluctuations in the early universe that would eventually collapse into stars and galaxies. As we race back across billions of light years, we watch the universe evolve in reverse. Galaxies become more numerous, younger, bluer. Structure becomes less pronounced. The era of peak star formation passes. The first galaxies disappear. We cross back through the cosmic web, through Laniakea, through the local group, until finally we see the Milky Way approaching. The Milky Way grows larger, resolving into individual stars. We plunge back through the galactic halo, across the disk, spiraling inward toward the Orion Spur. The sun becomes distinguishable, just one star among billions. We race past nearby stars, Proxima Centauri, Alpha Centauri, Sirius, until the solar system surrounds us. Neptune, Uranus, Saturn, Jupiter flash by. The asteroid belt, Mars, Earth-Moon system. Suddenly we're home, slowing, entering Earth's atmosphere, seeing continents and oceans, cities and forests, the whole beautiful, fragile, precious world on which life evolved and intelligence emerged. From the edge of the universe, Earth was invisible, lost in the glare of the sun, itself lost among billions of stars in a galaxy among billions. Yet this tiny world is where we live, where all human history has occurred, where everyone we've ever known has lived their life. It's our cosmic home, the only place in the universe we know supports life. Carl Sagan captured this perspective in his reflection on the pale blue dot photograph. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam. Our journey to the edge has given us this perspective. We've seen how vast the universe is, how small Earth is by comparison. We've seen that the universe is ancient, immense, filled with wonders, galaxies and quasars, neutron stars and black holes, cosmic web and void. We've reached the limits of observation and contemplated what lies beyond. Yet we return to Earth with renewed appreciation. This tiny world, insignificant in cosmic terms, is infinitely precious in human terms. It's where we live. It's where life has flourished for billions of years. It's where consciousness emerged, where beings appeared who could understand the universe, contemplate their place in it, and journey, if only in thought, to the edge of everything. The edge of the universe is far away, but it's also intimate. We observe the universe from here, from this particular place in space and time. The cosmic horizon surrounds us, equally distant in all directions, because we're at the center of our own observable universe. Everyone is at the center of their own observable universe. There is no privileged position, no special place. This is both humbling and comforting. Humbling because it reminds us we're not special, not central, not the purpose of the cosmos. Comforting because it means we're part of something vast and beautiful, connected to the whole universe through the web of space and time. As you drift toward sleep, let this cosmic perspective ease your mind. The concerns that loom large in daily life shrink when viewed against the backdrop of cosmic immensity. We live on a tiny world in a vast universe, our lives brief moments in cosmic time. Yet here we are, conscious, thinking, wondering, capable of understanding the universe that created us. The edge of the universe is far away, 46.5 billion light-years, a distance almost beyond comprehension. Yet it's also right here, because the light from that edge reaches us, carrying information about the early universe, connecting us to the most distant regions of space and time. Rest well, cosmic traveler. You've journeyed farther than light itself could travel in the universe's history. You've seen the universe from its largest scales to its oldest moments. You've reached the edge of observation, the boundary of what can be known through light. But you've also returned home, to Earth, to the present moment, to the here and now. The universe may be vast, but this moment is yours. The cosmos may be ancient, but you are alive now, able to contemplate it, to wonder at it, to appreciate both its immensity and your own small place within it. Tomorrow, the universe will still be vast, the edge will still be distant, the mysteries will remain. But tonight, rest in the knowledge that you are part of this cosmos, that you exist in connection with everything from the smallest atom to the most distant galaxy, that your consciousness is the universe becoming aware of itself. Sweet dreams, fellow traveler. May your rest be as peaceful as the deepest cosmic void, as refreshing as the birth of new stars, as restorative as the slow dance of galaxies through space. The universe awaits your continued exploration, but for now, simply be. Be here, be now, be part of the great cosmic story that has no center, no edge, no end, only the eternal present moment in which we live, wonder, and rest. Our journey has taken us from Earth to the edge of the observable universe, 46.5 billion light-years away. We've crossed the solar system in seconds, the galaxy in minutes, the local group in hours, the cosmic web over days, finally reaching the ancient light of the cosmic microwave background after a journey through all of space and time. We've learned that the universe has no center, or that every point is equally its center. We've seen that edge can mean many things, the edge of the observable universe at 46.5 billion light-years. The surface of last scattering, where the CMB originated, the cosmic horizon beyond which we cannot see. We've contemplated what lies beyond, more universe, perhaps infinitely more, forever beyond our observation. Now, let us return home. The journey back is instantaneous. We simply turn our perspective around. Suddenly, we're looking back toward the Milky Way from the cosmic horizon, seeing our galaxy as it was 13.8 billion years ago, not yet formed. Just density fluctuations in the early universe that would eventually collapse into stars and galaxies. As we race back across billions of light years, we watch the universe evolve in reverse. Galaxies become more numerous, younger, bluer. Structure becomes less pronounced. The era of peak star formation passes. The first galaxies disappear. We cross back through the cosmic web, through Laniakea, through the local group, until finally we see the Milky Way approaching. The Milky Way grows larger, resolving into individual stars. We plunge back through the galactic halo, across the disk, spiraling inward toward the Orion spur. The Sun becomes distinguishable, just one star among billions. We race past nearby stars Proxima Centauri, Alpha Centauri, Sirius, until the solar system surrounds us. Neptune, Uranus, Saturn, Jupiter flash by. The asteroid belt, Mars, Earth-Moon system. Suddenly we're home, slowing, entering Earth's atmosphere, seeing continents and oceans, cities and forests, the whole beautiful, fragile, precious world on which life evolved and intelligence emerged. From the edge of the universe, Earth was invisible, lost in the glare of the sun, itself lost among billions of stars in a galaxy among billions. Yet this tiny world is where we live, where all human history has occurred, where everyone we've ever known has lived their life. It's our cosmic home, the only place in the universe we know supports life. Carl Sagan captured this perspective in his reflection on the pale blue dot photograph. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam. Our journey to the edge has given us this perspective. We've seen how vast the universe is, how small Earth is by comparison. We've seen that the universe is ancient, immense, filled with wonders, galaxies and quasars, neutron stars and black holes, cosmic web and void. We've reached the limits of observation and contemplated what lies beyond. Yet we return to Earth with renewed appreciation. This tiny world, insignificant in cosmic terms, is infinitely precious in human terms. It's where we live. It's where life has flourished for billions of years. It's where consciousness emerged, where beings appeared who could understand the universe, contemplate their place in it, and journey, if only in thought, to the edge of everything. The edge of the universe is far away, but it's also intimate. We observe the universe from here, from this particular place in space and time. The cosmic horizon surrounds us, equally distant in all directions, because we're at the center of our own observable universe. Everyone is at the center of their own observable universe. There is no privileged position, no special place. This is both humbling and comforting. Humbling because it reminds us we're not special, not central, not the purpose of the cosmos. Comforting because it means we're part of something vast and beautiful, connected to the whole universe through the web of space and time. As you drift towards sleep, let this cosmic perspective ease your mind. The concerns that loom large in daily life shrink when viewed against the backdrop of cosmic immensity. We live on a tiny world in a vast universe, our lives brief moments in cosmic time. Yet here we are, conscious, thinking, wondering, capable of understanding the universe that created us. The edge of the universe is far away 46.5 billion light years, a distance almost beyond comprehension. Yet it's also right here, because the light from that edge reaches us, carrying information about the early universe, connecting us to the most distant regions of space and time. Rest well, cosmic traveler. You've journeyed farther than light itself could travel in the universe's history. You've seen the universe from its largest scales to its oldest moments. You've reached the edge of observation, the boundary of what can be known through light. But you've also returned home, to Earth, to the present moment, to the here and now. The universe may be vast, but this moment is yours. The cosmos may be ancient, but you are alive now, able to contemplate it, to wonder at it, to appreciate both its immensity and your own small place within it. Tomorrow, the universe will still be vast, the edge will still be distant, the mysteries will remain. But tonight, rest in the knowledge that you are part of this cosmos, that you exist in connection with everything from the smallest atom to the most distant galaxy, that your consciousness is the universe becoming aware of itself. Sweet dreams, fellow traveler. May your rest be as peaceful as the deepest cosmic void, as refreshing as the birth of new stars, as restorative as the slow dance of galaxies through space. The universe awaits your continued exploration, but for now, simply be. Be here, be now. Be part of the great cosmic story that has no center, no edge, no end, only the eternal present moment in which we live, wonder, and rest.